Well, hello and welcome back to Engineering 211 Statics. And what I want to do in this lecture is go over the first sample exam. So if you're having trouble finding that, I'll put a link to my web page in the description of this video. If you click on that and open at the left side there, if you open the tab or the subpage for Engineering 211, and then there's a subpage within that page which is sample exams. When you open that, you will find sample exam 1. And I encourage you, before you watch this video and before you look at the solutions, there's also solutions provided there to sample exam 1, that you print this exam out and give yourself an hour and see if you can do it. I think that's an important measure of your abilities. And if you then have trouble, you may want to look at the solutions and may then want to watch this video again. So if you haven't done that, I would highly recommend that you stop this video, that you go and do that, and you see where you stand on that. Now, once you've done that, and even if you do well on it, I would encourage you to watch this video, because I'm going to try and highlight a couple important points in the problem that don't necessarily come out well in the solutions. Gives you something else to think about as you look at these problems. So with that at hand, let's go ahead and get started. If the text is a little bit blurry on here, I've tried to blur this up some, but if the text is a little bit blurry, remember you can access the PDFs again through the website, and those should be a lot clearer. We've got problem number 1 here. We're given the following force system, and we're told that F1 is 100 pounds. We're told that F2 is 150 pounds. And we're told that F3 is 75 pounds. And that angle 1 is 55 degrees, that angle 2 is 30 degrees, and of course F2 is acting straight down. So you could do this with a geometry approach. If you did it with a geometry approach, you would add this vector to that vector to that vector, so you'd have 3 known sides and then the resultant, which is the 4th unknown side, and you would have, rather than a nice triangle that we could use law of sines and law of cosines on, you'd have a 4-sided figure. We tend to want to avoid that. So usually if we have 2 vectors, we might use a geometry approach, use a triangle to solve it. But if we have 3 or more that we're adding together, usually we go with an algebra approach, and that is just to sum up the x components and the y components. So if I look at summing the x pieces here, I'll go ahead and take positive to the right. I'm going to have the x piece here, which is 100 times the sine of 55, and this has no x piece, and this x piece is negative, so I'll subtract off 75 times the cosine this time of 30. Now, you have to be careful here, and these are some of the little things I'll point out that may not be completely obvious on the solutions, but a lot of times people get in the habit of thinking that, well, the x piece is always cosine. Well, no, it depends on where the angle is defined. Had we defined this angle in here, then it would be cosine. So if you go through that 100 sine 55 minus 75 cosine 30, that nets you 16.9633. I've got too many sig figs there, but for an intermediate solution, we'll just leave that. Then I could sum the forces in the y direction, and we'll go ahead and take up positive there. So I've got then 100 times, we'll say, the cosine. So again, because that angle is defined there, I'll use cosine. If you really don't like that, you can define this angle there and go back to cosine and sine for your x and your y. But I always just look at the triangle. So I'm looking at this side here. I'm going to take cosine 55. That would be positive because that's acting up. This is then acting straight down, minus 150, because that's all in the y direction. And then I need to find this side over here, which is going to be negative 75 times the sine of 30. So with that, I come up with minus 130.1424. And again, too many significant fingers, but since I wrote it out here, not keeping the memory of my calculator, I'll leave those. Let me double check that, make sure I have not, yeah, I think we're good. So now, we could, if we wanted to, we could write this in Cartesian form, that the resultant is equal to the x piece, 16.9 in the I direction, minus 130 in the j direction. That would be pounds. That would be a proper answer in Cartesian form. But it looks like we're requested to have our answer in magnitude angle form. So I'll go one step further with that. Put this on an XY coordinate system. So where are we on this XY coordinate system? 16.9. And then down here, way down here, at minus 130, I can plot f sub r. So f sub r would then have a magnitude that's equal to the square root of 16.96 squared. We take that and square it, and add it to 130.14 squared. We take that and square it. The negative sign goes away when you square it. So when you go through that, it turns out to be 131.24. Again, too many significant figures. But haven't got to my final answer yet. Does that make sense? It should be a little larger than that. This is so large, this is not going to affect it very much. So the number should be just a little larger than that. So I think I can have some confidence in that. Then if I find this angle here, which should be pretty close to 90 degrees, so we could talk about theta being the arc tangent. And again, I always just look at resolving this based on this triangle here. If I were to think of this triangle here, so I don't get hung up with the negative signs and whatnot. So we look at that as opposite, which is 130 divided by the adjacent, which is 16.9. So we're going to come up with 82.57. So then we have to figure out which one we have. Remember that we always measure the angle. If no one says anything about the angle, it's always measured positive, counterclockwise, from the positive x-axis. So if you end up, if we were to have found this angle here, we would have to designate that differently. We'd have to find the complement or something like that. So if you're not given a figure here or some other descriptor, we're always measuring from the x-axis, positive counterclockwise. Well, this says negative, so I'm measuring now that way. 82.5 and 131. That looks like that fits. Anything else? Wrong magnitude. Right magnitude, wrong direction. That would put us up there, wouldn't it? So that's wrong. That's wrong. So, and again, I gave you a little description of this on the electrical test that I went through. I realize not everyone's in the electrical, but E is always a poor choice. Oftentimes that's put there just to protect the process of making the test. If we've made a mistake in here, don't have the proper answer, then the obvious answer is E, and I don't have to, during the middle of the exam, say, oh, wait a minute, we need to add one more answer, and then it becomes fairly obvious that's the answer and whatnot. So if I have to guess, if I have to make an educated guess here, I'm going to always guess between A and D. I'm not going to say it's never E, but I'm not going to think of E first off. So answer A there. Let's move on. So a lot of questions here with this figure, questions 2, 3, 4, and 5. And I'll do one with each of the figures. I think I mentioned to someone that I like this figure. It took me a long time. I actually drew this in paint, so I like to use it a lot because you put a lot of effort into making it. So we're told the D dimension is 1 foot, the H dimension is 2 feet, and the width dimension is 3 feet. And then we're told if the magnitude of T1 is equal to 100 pounds, so that's 100 pounds, T2 is equal to 0, so that really doesn't even exist, and the moment is equal to 0, that doesn't exist. We would like to find T1 as a vector. Okay, so we know that we could express T1 as a vector as its magnitude, whatever its magnitude is, times the position vector that's represented by it. Well, that would be from C to A, right? R from C to A, divided by the magnitude of said position vector. So what do we have here? Do we have the magnitude of t? Yeah, absolutely. That's 100. And I need to multiply it. How do I get from c to a? Well, you could parameterize c in terms of the set of x, y, z for c and the set of x, y, z for a, and take the a points and subtract the c points. I usually just imagine myself standing at c and give myself instructions on how to get to a. So how would you do that? One thing we have to be careful of, it looks like the coordinate system has been rotated here. It's still a right-hand coordinate system. You take x and go to y, and your thumb's pointing at z, so it's still a right-hand coordinate system. But this is a little unique with this x up here. So I'd have to go, what, -2 in the -2 in the I direction, or the x direction. That's going to put me here. Then what do I have to do? I have to go 1 in the y direction. That puts me there. And then I have to go 3 in the z direction. I'm going to divide this thing by the square root of 4 plus 1 plus 9, right? Now you could convert, if you wanted to, you could say, take this as the unit vector representing the direction from C to A. And I actually did that in the solutions and went through that. But probably this is just as well. So when you do that, what do we come up with? So I get minus 0.534 in the I direction. And positive 0.267 in the J direction. And then 0.802 in the K direction. Now this is just this portion right here. So that is actually the unit vector. So if you wanted to, we'd really need to multiply that by 100. So I'll put that 100 here. There we go. We'd multiply that by 100. So if we need that unit vector in the future, we have that. That might be useful. So find T1 as a vector. So I just multiply this thing by 100, right? So minus 53.4 in the I direction, plus 26.7 in the J direction, plus 80.2 in K direction. So we should have something like that. Which one does that turn out to be? Minus, it's not that one. Minus 53, positive. Yeah, it looks like our answer is B, doesn't it? That one would be wrong from the negative sign. Yeah, that one's a little bit off on those. So answer is B there for 2. Good. Well, just warming up. So we've got 2. We've got then 3 to do. So again, we take this as 2 feet and 3 feet and 1 foot. And then we're told if T1 is 0, so that's removed. T2 is 500, so that guy is 500. And the magnitude of this moment is 250. And it's shown in the direction there. Find the moment about point A. Okay. Well, we could say that the moment about A is going to be equal to R crossed with F plus whatever moment we have here. So let's put this in the context of our problem. what is R? Well, I'm going to have to take, if I'm finding the moment about A, right, that's going to be this R. So I'll just go ahead and leave that as R because I've indicated that there. Crossed with T2, there's our T2, plus the moment about C. So what are we going to have here? What's R? Well, that R is simply what? I have to go 3 in the minus Z direction. So I'll say minus 3 in the K direction. And I'm going to cross that with T2. Well, T2 is all in the X direction, so that's 500 in the I direction, isn't it? And I'm going to add that to the moment about at C, this M sub C. Well, this axis here, this is the Y direction, isn't it? And I take my right hand, use your right hand, put your fingers in the direction of that arrow, and which way is your thumb pointing? Am I getting that right? Let's see. I got that. There we go. So my fingers go in that direction. They're wrapped around that axis like that, and my thumb is pointing back this direction. So if I were to write MC, there is the direction of that moment. So it's in the positive Y direction. So I could say that this is 250 in the Y direction, the J direction. So this comes from the positive Y direction. Okay. So I go through the arithmetic here, and I come up with what is this is minus 1500, 3 times 500, and then what's K crossed with I? Remember I, J, K. We look at K crossed with I gives me J, and then I have to add to that 250 J. So that's negative, that's positive, so that turns out to be equal to what? Minus 1250 J pound-feet. So minus 1250 J pound-feet. The answer there is C. Now a couple of things with this. No matter where we took the moment about, if I took the moment about B, this term would be different, but this would be the same. This moment up here, this is a free vector. And it's going to have to be added in everywhere. And that's going to have an effect on the equilibrium problem that we get to in a little bit, and that's one of those things that I thought even if you got to this answer, you might want to listen to this video to help you deal with that. No matter where we sum the moment about, this point, this point, this point, a point out here, that's a free vector and has to be added in the same. Well, good. So we've got question number 3 done. I guess the last thing, this, I mean, if you're uncomfortable with how I came up with that, that would be really the same as I, J, K. What do we have? 0, 0, minus 3, and then this was, what, in the I, 500, 0, 0. You could go through that if you wanted to. I think it's just easier in this case to just do the multiplication, and K crossed with I is J. Well, I think we're good there. Let's move on to question number 4. So again, we have the same dimensions here. This is 2 feet, 3 feet, 1 foot. And we're told if the magnitude of T2 is 500, again 500, find the projection of it on the line from A to C. Okay, from A to C. Well, do I have that? Yeah, I mean, you could get that. You could come up with the unit vector for A to C. You could get that as the position vector A to C divided by the magnitude of that same position vector. And where would you get this? You could take the points for C points, the X, Y, and Z, and subtract the A points, X, Y, and Z. if you wanted to. Okay, so you take the points at the end and subtract the points at the beginning and get that position vector. Well, we've done this before. This looks vaguely familiar. The only difference is I went from C to A, right? So I could say that the unit vector for A to C is really equal to negative the unit vector C to A. Do I have that one? There's the unit vector C to A right there, isn't it? So I could say that this was positive because of the negative sign. This term, 0.534 in the I, negative 0.267 in the J, negative 0.802 in the K. Okay? So I took this position vector that I got here and I put a negative there, then, or negative and negative became positive. That's negative. That's negative. Okay. Now, if you wanted to go through it with this, that would be just fine. That'd be good practice. But if we're in a hurry, like we might be on a test, this is good. So we've got then find the projection of it on the line A to C. So what I need to do is I need to take this T2 and I need to dot it with the unit vector AC. So what's T2? That's really just 500 in the I direction, isn't it? So I have 500 in the I direction dotted with the unit vector A to C, which is going to give me 500 times what? I just look at the I term, 0.534, which gives me 267. Let me double check that. Yeah, 267. Okay, so 267. Hopefully I have that answer there. Good. Okay, and a lot of people say, well, if you use this previous answer, if you had a mistake there, you'll carry that mistake over. And that's true. And then sometimes that's a disadvantage. But also, if I didn't get an answer here, that would be a good sign that maybe that's not right from the previous problem. If I had time, I should probably go back and check that. But you could, again, if you had time, go through this process and you should get exactly the same answer. Okay, so our last question here on this one, question number 5, is, again, we have 2 feet, 3 feet, and 1 foot, and we're asked, what is the angle between T1 and the line from C to B? Okay, so there's this line from C to B, and I'd like to try and find this angle in here. Okay, that's what we're looking for. Well, remember that we could get theta is equal to the, in general, the arc cosine of vector A dotted with vector B divided by the magnitude of A times the magnitude of B. Or we could say that this was the arc cosine of the unit vector for A dotted with the unit vector for B, because that's essentially what you have there. Well, do I have the unit vector for this line from C to A? I do, don't I? This was right there. There's the unit vector from C to A. So I had that as, so the unit vector for this one, this will be the unit vector for T1, would be what we started with there from C to A, and I could go back to the previous page and get it, or I just know it's the same as that with a negative sign, so minus 0.534 in the I direction, plus 0.267 in the J direction, plus 0.802 in the K direction. So there's that one. Now the unit vector for this one here, that's going to be the unit vector from C to B. So the unit vector from C to B, we could say, was the position vector from C to B divided by the magnitude of that position vector. So what's that going to be? Imagine yourself at C. And again, you could take the points at B and subtract the points at C, but I would just imagine myself at C and give myself instructions on how to get to B. I'm going to have to go -2 in the, what am I going to go? -2 in the x direction, plus, that puts me right there, +3 in the k direction. You'll notice that it's contained in the xz plane, so you have 0 in the y direction. So I'll then divide this by 4 plus 9, which gives me -0.5547 in the I, plus 0.832 in the k. So now I'm going to take that, I want to take this unit vector here for T1 and dot it with the unit vector for CB. So I'm dotting this with that. What do we come up with there? I'm going to have -0.534. That's the I piece here. And then I'm going to have -0.5547. I have to add to that. There is no y piece here, so I needn't worry about that. And then I'm going to take this 0.832, and I'm going to multiply that by 0.802. When I total that up, so right now I'm just figuring out what that is. Negative and negative becomes positive. So I get 0.9635, and that's in the argument of the arc cosine. So I do the arc cosine. So take the arc cosine of that. Gives me 15.5 degrees. Let's see, is that an answer? Yeah, right there, D. Good news. Okay, D, 15.5 degrees. Good. This one wouldn't be too tough to do without doing any work, because, let's see, it's probably not, I mean, if we just look in here, it's not that big, not that big. I mean, you could spend a little time hemming and hawing about whether it's these two, but you get to narrow it down, and again, like I said, E is never usually a very good guess. This one I also showed you how you could, if you look at the solutions, you could look at a triangle here. And I wouldn't always bank on this. Sometimes it's going to be a lot harder to do this, so I would make sure that you could go through this. I think this is always going to work for you. But in this problem, you recognize that if you look at this as a right angle here, you have 1 there, right? And then this side is just going to be the square root of, what, 3 and 2 as the sides, 3 squared plus 2 squared. And there is your theta. So I could look at the arc tangent of 1 divided by, what do I have? 3.605. 15.5. Yeah, you get the same answer. So that would certainly be a lot faster, although I wouldn't bank on that if someone gives you a kind of an ugly problem. This may be a lot easier. So hopefully some good insight in that. The exam itself will usually have something like this where we develop a situation, ask several questions on it. We'll try not to have them too intertwined. So if you make a mistake on one, hopefully you can get the others right. But sometimes they're a little intertwined because you don't want to have to develop a separate problem for each problem, because then a multiple choice test either turns into a test with only 4 questions, which is kind of ugly for multiple choice, or it gets way too long. Well, let's continue on. So we've got, using the following figure, answers questions 6, 7, and 8. If F is equal to 500 pounds, and M is equal to 100 pound-feet, and L is equal to 8 feet, that would mean that you'd have 4 feet there, and likewise then 4 feet there. Find the vertical support reaction at A. So this is Chapter 5 material. A lot of times that's kind of the difficult thing, is to figure out, well, I'm given this problem, particularly on the final. It came from the entire term. What technique do I use on it? Well, this is totally Chapter 5. Equilibrium. So I draw a free body diagram of this thing. So what do we have at A? I have a pin, so I'm going to have y is going to be in the vertical, and then let's see, I got AY acting up, AX acting horizontally. I've got then B, I'll just say B because it's a roller, I only have one of them. We've got 500 here acting down, 4 feet, 4 feet, 8 feet, and then we have this concentrated moment out here on the end, 100 pound-feet. So proper free body diagram is important. I think that's a proper free body diagram. We'll go ahead and take X to the right and Y up. And our question is, find the vertical support reaction at A. Well, let's see. How could I do that? Well, if I sum the moment about B, setting that equal to 0, what am I going to have? Well, I've got this 100. I'll go ahead and take clockwise as positive, so I have to add in this 100. And this is huge. Again, that's a free vector. That has to be added in no matter where we're summing the moment about. Down here, I'm going to sum the moment about A. Okay, and we'll have to put it in that equation too. I'll sum the moment about B here. I can say that that's 100 plus summing the moment about this point here. That'll be AY times 8, and then minus, this tends to rotate it counterclockwise, minus 500 times 4. So I can say that AY is equal to, solving this equation, 500 times 4 minus 100 divided by 8. What do we come up with there? So we've got 237 pounds. Yeah, 237. So an answer, pounds up, down. Let's see, it's positive. We drew this positive, so it would be up. So the answer would be A. Now I get down here, and I could sum the moment about A. Let's see what that looks like. I've got 500 times 4, summing the moment about this point. 500 times 4, and then I have to add this 100 plus 100. Now you don't have to multiply this by distance. This is already foot-pounds. This is pounds here. This is feet here. This is pound-feet there. You just include that in. If you're summing the moment about here, if you're summing the moments about there, if you're summing the moments about here, if you're summing the moments about there, you have to add that in. It's free vector. Now I'm going to have to do what? I've got 500 times 4 plus that 100, then minus, because I'm going the other direction with this B, minus B times 8. So I could, solving this, solve for B. B is equal to 500 times 4 plus 100 divided by 8. How do you get 262? 262 pounds. That's positive, so our direction was correct. It's up. So, because we assumed it up, it became positive. It was up. If we assumed it up and we got a negative sign, we would know it was down, but we assumed it up. We got a positive, so it's 262 up. So we get answer B. Now in the solutions on the problem, I actually did this equation, you'll see, and then I said, well, I'm going to go ahead and sum the forces in the vertical direction. Summing the forces in the vertical direction, setting those equal to 0, y being the vertical direction, I have AY plus B minus 500. That's a moment. That doesn't show up in the force equation. So I just have this force up, and that one down. This one doesn't show up either because it's horizontal. So then once I had got this answer, I put the 262 in here. So I had then that AY was equal to 500 minus 262. So what do we get there? 237. And I came back and got that one, and that's fine. What about this AX? Well, we recognize that that's 0 very quickly by summing the forces in the x direction, setting that equal to 0. What forces do I have in the x direction? AX. There it is. Okay. So lots of ways to do this problem. The biggest thing, and that's why I think that probably watching this video, unfortunately people that chose not to watch it may miss out on this, but the free vector, this is huge. You've got to put that 100 in there. You've got to put that 100 in there. No matter where you sum the moment about, you have to add that in. Okay, so we've got 6 and 7. What do we have here with 8? So I'm going to quickly reproduce my free body diagram. Presumably, if you were doing the test, you would just refer back to that page. So I've got AY, AX, B, this is F is 500, this is 4 feet, and 8 feet. And we put the moment on like this. And what are they wanting here? Find the magnitude of M to produce a 0 vertical support reaction at A. So we would like this to be 0. We know that's 0. It's from sum of the forces in the x direction is equal to 0. It is equal to AX. But we'd like to get this one 0. Well, what could we do? We could sum the moment about B, right? So if I sum the moment about B, setting that equal to 0, I have what? I have AY. Did I write that? Yeah, okay. So I've got this M. So I don't know if this is 100 anymore, so I'll just say that that's M plus AY times 8, because I'm summing the moment at this point. So I've added that, and then I'm going to subtract off 500 times 4. Okay, so I could say then that M, well, we said this AY, we're hoping this is 0, right? So we sub in 0 there, and we get 0 is equal to M minus 500 times 4, or M is equal to 2,000. Moving that to the other side, yeah. Do we have an answer there? Yep, B. Okay. So what we did is we set this one equal to 0, and hopefully that makes sense. You're just going to teeter that about that point there. Okay. Good question to follow up on this is, what would the reaction at B be at that point? Well, it'd have to be 500 if you sum the forces in the vertical, wouldn't it? Okay, so we've got 2,000 there. And again, we had to put that in. There's that free vector right there. Wouldn't have made much sense if we didn't add that in. Well, the last two questions here, 9 and 10, using the following figure to answer the questions 9 and 10, take F1 equal to 100 newtons and F2 equal to 200 newtons and F3 equal to 300 newtons. We've got our dimensions there. We notice we've got a problem right there, centimeters and meters. I don't like that. I'm going to change that to 0.9 meters right off. Okay. So dimensional homogeneity, we've got the problem stated, we're good to go. We'd like to find the magnitude and direction of the moment at point A created by the forces. So what we are really asking, and this goes back to some chapter 4 work, is if we were to look at cutting off this beam right here, having this little stub of a beam, and we've got point A there, there would be some shear force. That's the equivalent force. Okay, that's the sum of all the forces. And then we would have the moment here, which would be the sum of all the moments, wouldn't it? Okay. So maybe I'll do 10. Find the magnitude and direction of the equivalent force. Okay. Well, let's see. I could, and this force, I've drawn it down, but it looks like it's probably going to have some horizontal pieces because it's got vertical pieces and horizontal. So maybe you might say that that's some of the forces F in the vertical, and we could have some of the forces in the horizontal. So I really just need to resolve these forces. So if I take this, I could sum the forces in the x direction, which would be 100 times the sine of 20. Is that right? Yep, that's going to the right. We'll take positive to the right. Minus 300. Anything else in the horizontal? I'm not trying to find the reaction here. I'm just trying to find the equivalent force acting there. So this turns out to be minus 265.798. So intermediate step, we'll keep quite a few digits there. If I sum the forces in the y direction, looking at positive up, what am I going to have? 200 minus 100 cosine 20. I think that's it. Okay, so 106.03 is what that turns out to be. So I could plot this if I wanted to. What I'm going to have here is on my x minus 265, and on the y 106. And there is that reaction right there. So the magnitude of it turns out to be the square root of 265 squared plus 106 squared. You'd want to keep more decimal places in there, but probably in the memory of your calculator. The negative's not a big deal because it's going to go away when you square that. So that turns out to be 286.2. And then the angle here, we could find this angle in here if we wanted to, and then we'd add that 90 to it to get that. So when you go through that, you would have the arc cosine of this opposite side, 267. I mean, not arc cosine, arc tangent of what this one here, if we're looking at that one, call that alpha. 265 divided by this one, 106. Double check that. So that's 68.1. When I add 90 to that, I get 158. Yeah. So 68 degrees. And that's at that angle there, and I want to define it from over here, so I'm going to say that it's, because we always define it from the x-axis, so I'm going to add 90 to that. So when you add 90 to that, you get 158. So what's our answer? 286 at 158. Looks like even with just the magnitude, this would be the answer, and we get 158, so that's good. We got A there. Now, what do we need to do? We need to find this moment, don't we? So I think I will go ahead. In the solutions, I actually summed the moment, and I used this way as positive. And you can look at that. Maybe I'll do this a little bit differently here. Mix it up a little. I'll go ahead and take positive or clockwise as positive, and I'll look at seeing what the moment is. And we're not setting this equal to 0. We're not doing equilibrium. We're just trying to find the equivalent, what all of these add up to. So I'm going to have this, let's see, 100 times the cosine of 20. So that's that piece there, which acts through 0.9, minus 200 times 1.9. That's that, acting through that total distance. And then this piece here, we'll assume that this beam is pretty thin, so that this piece that's acting right there doesn't act through much distance, and certainly this intersects that point. So really all I have to do is worry about the vertical piece of this and that. So what are we going to come up with? Minus 295 Newton meters. Now the negative indicates that it's opposite of that, so I would say it would be 295. What's opposite of clockwise? It would be counterclockwise. So 295 Newton meters counterclockwise, because we took, this is negative clockwise, so it would be positive counterclockwise. So the answer would be D there. And again, what you have solved for here is you've solved for, now we know a little more about this, I can update this drawing here. Back over here at this support, there's that point A, and what do you have? Well, you have a force that looks like this, that's 286, acting at an angle of, what was that, 158. That's the equivalent force. And then the moment is going to be like this, which is 295 Newton meters. Did I say pounds? That should be newtons, shouldn't it? Make sure I've made that mistake anywhere else. Newtons. Hopefully if I've said pounds, you have edited that as newtons. This is a metric problem. Newtons. Okay, so that's the equivalent of these. This is not an equilibrium problem. This is a chapter 2 problem or a chapter 4 problem, most likely a chapter 4 problem. The force part is chapter 2. The moment part is chapter 4. We're not talking about chapter 3 or chapter 5. We're just trying to find what these all add up to, and that's what they add up to. Now, if you wanted to find the reactions, the reaction that you had to have there, it would be opposite of that. Okay, so let me double check this. 295 counterclockwise and 286 at 158. Yep. Okay, well, so I think that gets us to the end. Yeah, question number 10 gets us to the end. So spend some time going through this. Again, print out the blank exam again. See if you can sit down and go through these, because the test itself is not going to have exactly the same problems, but conceptually they're going to be very much the same. And you want to make sure that you have a good understanding of this. Well, I will leave with that. When we get together next time, we're going to go on and talk about equilibrium in 3 dimensions. We'll do a problem on that, and that will then lead us into Chapter 6, which deals with trusses, and that will be a fun as we advance into that. So take care till then, and thank you for watching.